Welcome to today's deep dive. When you look at a highly polished transmission gear, it just looks so serene, like it just popped out of a mold, perfectly formed.
Yeah, it really looks effortless, placid even.
Right, but to get that perfect piece of metal, you actually have to subject it to absolute violence. I mean, explosions, acid baths, electromagnetic torture.
Oh, absolutely. It is a microscopic war zone on the manufacturing floor.
So today we're diving into the absolute extremes of that manufacturing physics. We are decoding 5 crucial precision transmission terms to understand how all this works.
Because mastering these terms is basically your shortcut to sounding like a 20-year R&D veteran on the floor.
Exactly. We're looking at how engineers use dramatic, localized energy to alter metal physics, starting with induction hardening.
Right, which uses an electromagnetic field to rapidly heat just the outer layer of a part, like output shaft splines.
Which boosts wear resistance. I always picture this like baking the perfect artisan loaf of bread. You want that crust super crispy to handle the friction, but the inside has to stay soft and chewy.
That is a great analogy. The softer inside matters because transmission shafts deal with immense torsional twisting.
So if you harden the entire shaft, it would just become brittle, right? Like a massive torque spike would just snap it in half.
Precisely. Induction hardening maintains that crucial core toughness. You need that to physically absorb the shock.
Okay, so electromagnetic fields give us precision heat. But what if precision isn't the problem? Say you have a massive engine block with these twisting oil channels drilled deep inside.
Yeah, you can't exactly get a mechanical tool in there to smooth out the rough edges.
Right, the hidden microbursts. So what do?
That is where you abandon localized heat and move to explosive heat. It's called thermal deburring.
Wait, we literally just blow things up. How does the engine block even survive that?
Well, you fill the internal cavities with a combustible gas mixture and just ignite it. Boom.
Wow. Just an instant explosion inside the part.
Yeah, the explosion creates a temperature spike so fast and intense that the tiny high surface area burrs instantly vaporize.
And the main block is fine because it's just so massive.
Exactly, it barely gets warm. It is by far the most efficient way to clean inaccessible internal channels.
Okay, so the metal survives being torched and blown up. But a transmission requires components that fit perfectly.
Right, like finishing the pinholes on a planet carrier.
Yeah, I've seen specs demanding sub-micron true position for those. We're talking smaller than a speck of dust just to get these planetary gears aligned.
And to achieve that, you rely on jig grinding.
Because if those pinholes are off by even a fraction of a hair, what happens?
The entire transmission system vibrates and literally tears itself apart under high RPMs. That's why jig grinding machines operate in strictly temperature-controlled environments.
Just to chase that ultimate hole position and size control. But grinding still uses friction. What if the part is too delicate, like tiny microgears?
Yeah, mechanical polishing would rub and bend the surface, rounding off sharp edges.
And it would introduce mechanical residual stress, right? So how do you avoid that?
You switch entirely to electrochemistry. Electropolishing. You submerge the gear in an electrolyte bath and run an electrical current through it.
Okay, I have to stop you there. We're intentionally dropping our perfect gears into an acid bath.
We are, but it's a process called anodic dissolution.
How does the current know to only dissolve the rough spots and not eat the entire gear?
Well, the electrical current naturally concentrates at the microscopic peaks on the metal surface, the rough spots.
Oh, so it selectively dissolves those peaks away.
Exactly. It leaves a mirror finish with zero mechanical residual stress, while those crucial sharp edges stay perfectly intact.
That is incredible. But electropolishing is for microcomponents. What about the massive complex housings?
Right, you can't just drop an entire transmission casing into an acid bath.
And grinding a hardened complex shape takes days. So what's the modern solution?
Hard milling. Instead of grinding, you take a milling cutter to something with a hardness of HRC 50 or above.
Wait, milling hardened steel, wouldn't that metal instantly shatter a standard drill bit?
It totally would. But by using ultra-rigid machine tools and advanced ceramics, you can carve that hardened steel almost like it's aluminum.
So you harden the part first, then mill the final shape, completely skipping the grinding bottlenecks.
Yeah, it shaves days off the production cycle. It fundamentally shifts how you look at the manufacturing journey.
It really does. For anyone listening, these aren't just vocabulary words. This is a map of how human engineering pushes physical limits through extreme heat, electrochemistry, and submicron friction.
It is absolute mastery over the material.
Which brings up a fascinating question for you to ponder. If we are already vaporizing metal with gas explosions and dissolving it with electricity just to perfect microgears, what happens when we reach the absolute atomic limit?
Will we eventually stop subtracting metal entirely?
Exactly. Will we just figure out how to grow transmission parts atom by atom? Something to think about next time you look at a perfectly polished gear.